Let's get back to the second part, that is reconstructing the signal given the samples. We have the samples G of n by 2w. From that, we have to get back the signal G of t. So this is at the receiver end. And let's see how we can do this. We started off with this in the morning. I asked you to apply the inverse Fourier transform to the given function g of f. Whatever g of f we had obtained in equation 7, I wanted you to get the inverse Fourier transform for that. So the limits from minus infinity to plus infinity would change to minus w to plus w. Did you try the derivation? And what is the expression you're getting? So in this part, we have just substituted what was g of f. G of f as per equation 7 was given as summation n is equal to minus infinity to plus infinity g of n by 2w into e to the power of what? I think we had only j pi nf by w, right? J pi nf by w. 2 wasn't there, I think. Into e power j 2 pi ft df. This was the expression. You can just...
Excuse me, ma'am.
Yeah.
I mean, those expressions you showed, I guess something is wrong there.
In which one?
It should be the one you are showing right now when you started. Reconstruction.
Yeah, 1 second. Okay, this is g delta of f.
Yeah,
And
yeah.
what was g of f? What was the expression for g of f we got? This one, right? 1 by 2w summation g of...
Exponent is j pi nf by w, but that was not what was given in the that reconstruction part.
Yeah, that's what I'm checking. 1 second.
It is given as 2 pi nf. It is not.
Yeah, that
The
2 is not there. Remove that 2. I want you to substitute whatever we have used and tried. See, I just now sat and solved, because you people are not solving anything. I just wrote the whole thing. Can we just go through this and see? So according to what was written, g of f was written as 1 by 2w. I'll just use a different color. Okay, this was g of f. And the inverse Fourier transform g of t is defined as g of f into e power j 2 pi ft df. We know this. Now, we had g of f given, this was equation 3.7. 1 by 2w summation g of n by 2w e power minus j pi nf. We did not have 2. Yeah, you're right. By w. Now, how do I get g of t? All you have to do is substitute this in this and simplify. That's what I asked you to do. See, substitute this g of f in this expression 1. So all what we are doing is using equation 2 in equation 1. Okay.
we get sync function.
Yeah, you should get a sync function. If somebody has derived and got, it's good. How many of you have at least tried? Okay, at least go through this correctly. It's all simplification, nothing else. This is nothing. Actually, this need not be part of the derivation. But you can't remember the successive. If you remember the successive equations, you can skip all this and write. Otherwise, it is usually difficult to remember directly. So we'll get that expression by substituting. All you have to do is simplify this. So we know the limits for integration have to be applied between minus w to plus w because the signal exists only between these values. 1 by 2w, I have substituted the value of g of f here into e power j 2 pi ft df. We have exchanged the summation and integration, and g of n by 2w is a constant. It is the weight or constant. It is taken outside, okay, because it will not change. It doesn't have the variable f. Remember here the variable is f, the frequency, and it is not there, so it will represent a constant value or the scaling factor. Now what do I have within the integral? Within the integral, what is remaining will be e power minus j pi n f by w into e power j 2 pi ft df. Here, let me take the common factors outside. It is e power something into e power something else. I can take minus jf as the common factor. You see here, I have simplified taking minus j as a common factor, then
It should be
n pi
minus 2 pi
by
t.
w, and f is also taken. Yeah.
It should be minus 2 pi t.
This will be minus j if it is common. Yeah, minus of minus j. This will become 2 pi t, right, into f. Fine. Then 1 by 2w summation, again all this is left, minus j n pi by w, again this will be minus 2 pi t. Yeah?
Yes, ma'am.
Okay. And f, this will become minus the integration of this. So what is,
And is it that small g of n by 2w?
no, we wrote capital G only there, right? We wrote small g or capital G.
I guess it is small g. I
Okay,
have
I don't
written small.
remember what we wrote there in that small g of n by 2w. No problem. Anyway, it is a constant, so you keep it as whatever you have written. I thought we have written as capital, so I took. So this is small g only then. Okay, just change it. It doesn't make a difference. Anyway, it is just a constant. Only this had been taken as plus by mistake. It should be minus. And here, after integrating, I have e power integral e power j theta is e power j theta divided by whatever is the coefficient. Okay, that coefficient I have written below, and I have to uh, substitute. This is into f. So I have to substitute what? For f, wherever I have f, I have to put the limits plus w and minus w. That's the next step. Is this okay? Just go through the steps and see if there are any other mistakes. G, this is e power. Will it be minus j? We are taking 2 pi f. Jf is already there outside as common. I want to take out 2 pi also. So what is left in this term? In this term, only t will be left, second term. So when I take this as common, what is left here? 2 pi also I'm taking outside, so only t is left out. And in the first term, I have pi taken out, so n by 2w. Should I get n by 2w?
Yeah, ma'am. N by 2w.
Yeah, this becomes n by 2w. Okay, so this is j 2 pi. Again, in the denominator, we are taking the same common terms, j 2 pi outside or minus j 2 pi. So this becomes From the second term, I'm going to get plus t. And from the first term, I'm going to get n by 2w as the common factor. Now I can substitute for f as plus w and minus w. We'll do it in the next step. So the same thing we have written here. Okay. I think where did I have minus sign? I should take minus. Okay. Plus w and minus w. This is n by 2w. We'll take out this. The denominator is a constant. Let it come out. Okay. And the numerator, I should have e to the power of, I think this will be e power minus j 2 pi w into t minus n by 2w minus of e to the power of plus j 2 pi w. Correct. So first I'm substituting plus w. So this is a minus. Then I'll substitute minus w. It becomes plus. So I have one positive and one negative. If I take this negative sign inside, see we have a negative sign outside. That one step you should, when you take this negative sign inside, what happens? This becomes minus and this term becomes positive. Is that clear? There was a minus here. That minus, I have taken it inside these brackets. After substituting for f as w, plus w and minus w, I have taken this minus sign inside. So this first term which was positive becomes negative and the second term which was negative becomes positive. Now, if you just take this, this is in the form of e power j theta, this is in the form of e power minus j theta divided by 2j. If I just consider this 2j, what will I get? It becomes sine. Yes or no? What is a sine function? Sine theta is e power plus j theta minus e power minus j theta by 2j. All of us remember this, right? So we are using that condition here. This whole term inside is e power minus e power minus j theta plus e power plus j theta divided by this factor 2j. If I take, that becomes sine of, now I'm just multiplying the terms, sine of this j will be kept out anyway. This is only sine theta, right? So sine of 2 pi wt first term minus 2 pi w into n by 2w. So 2w, 2w cancels. I'll get pi n. Correct? See, you just multiply these terms. How much is 2 pi w into t minus n by 2w? This becomes 2 pi wt, the first term, minus 2w cancels here. What is left is minus pi n. That's what is written here. Okay. Sine 2 pi wt minus pi n. In the denominator also now I have a positive value. So if I already we have a 2w outside here, that 2w into what? Pi into t minus n by 2w we have. This j has gone. This 2j has gone. What is left out here is just pi. With this pi, I'm clubbing this 2w. That's how this 2w has come here. Okay, nothing extra. Hope you are following the steps. If you haven't done already, please just, all what we are doing is substitution and simplification, nothing extra. I'm trying to compute that integral. Next, I should try to bring it to the form of sine theta, sine of pi theta by pi theta. I want to bring it to that form so that I can replace this with a sinc function. So what do? Let's multiply this inside. If I take this 2w again as the LCM, we'll have this as 2w pi t, the first term, minus n into pi. We already have a pi, and that 2w again comes outside. I have what? 2w left out because that is the, and the LCM here will generate a 2w here. Okay. So finally we end up with the form sine pi theta by pi theta, or sine pi t by pi t, which is in this form, and that can be written as a sinc function. Sine pi t by pi t can be written as sinc 2wt minus n, and this is small g of n by 2w. Sorry, all this should be small g. Okay, and that is what we have obtained here. If you see the end result, he directly
Ma'am,
gives you,
will have pi no, ma'am.
yeah,
Sync also will have pi no, because sin x by x is sync.
sin x by x, no, sin pi x by is sinc. Sin pi x by pi x is sinc, not sin x by x.
Okay.
Sin pi x by pi x is sinc x. Okay. Remember this. Sin pi x by pi x is sinc x. So you will get it in the form of sinc of the angle. So that sinc of angle, in the end, we got this sinc 2wt minus n into g of n by 2w, where t lies between minus infinity to plus infinity. This is known as the interpolation formula, and this shows us how we can reconstruct or get back the original signal from the samples g of n by 2w. Okay, so let's see. So this is an interpolation formula for reconstructing the original signal g of t from the sequence of samples denoted by g of n by 2w. Okay, so the sinc function, sinc 2wt, is playing the role of the interpolation function. Each sample is multiplied by a suitably delayed version of the interpolation function, and all the resulting waveforms are summed up to obtain g of t. Okay, these are the things which we what which we can infer from the given. Yeah, the formula which we have here is known as the interpolation formula. You know what's the meaning of interpolation? What's the meaning of the word interpolation? In maths, we use the term interpolation for an estimation function. We use some statistical methods or any other polynomial estimation, statistical estimation, any kind of estimation. When we use it in numerical analysis, this interpolation will provide the way of estimating using the sequence of samples. That's why this is called interpolation. From the samples, we are getting back the function. Okay. So that sinc function acts like the interpolation function. And every sample is multiplied by a delayed version of this sinc. As you can see in this expression, every every sample g of n by 2w, as n changes, if g of 1 by 2w, 2 by 2w, whatever, each sample gets multiplied with this sinc, different delayed versions of sinc. You see the sinc function also has n. Okay, so it will be multiplied with the delayed versions of the sinc waveform or the interpolation function, finally resulting in the required signal g of t. Okay, so based on these results, we will redefine the sampling theorem a little more specifically. Okay, let's try to redefine this. A band limited signal of finite energy, which has no frequency components more than W hertz, can be completely described by specifying the values of signal at instants of time separated by 1 by 2W. That means you always have to sample at a rate which is twice the highest frequency component of the original signal. So we have already considered this as our initial sampling theorem. We'll add one more statement. Band limited signal of finite energy, which has no frequency components higher than W, can be completely recovered from a knowledge of its samples, which are taken at a rate of 2W samples per second. So I'm going to sample at a frequency rate of 2W samples per second. Then I can completely recover the original signal. That is the second part of sampling theorem. So the first part is getting the samples from the given signal. The second part is how to reconstruct back the original signal from the samples. So for both cases, we are telling the sampling rate should be 2W samples per second minimum. Anything higher than that is good. Okay. And the sampling time also should be 1 by 2W. Note, sampling rate of 2W for a signal of bandwidth W hertz is known as the Nyquist rate, because all this was formulated by Nyquist. And its reciprocal 1 by 2W is called the Nyquist interval. So whenever the time period T takes the value 1 by 2W, we call it as Nyquist interval. And the derivations of sampling theorem, which we have done so far, were based on the assumption that the signal G of T is strictly band limited. Only then we could get that relation between G of F and G delta of F. We could relate G of F with G delta of F easily because it was strictly band limited. But practically, it's not possible to have strictly band limited signals, and the result is under sampling. So if you don't have properly band limited signals, we have something known as undersampling, and we have another effect called as aliasing effect. Let's see what is this. Okay, very important. They'll ask you what is aliasing even now and even in your 6th semester when you study digital communication. This is an important side effect which has to be overcome. So aliasing is the phenomenon of high frequency component in the spectrum of a signal taking on the identity of a lower frequency in the spectrum of its sampled version. See, when I don't have a properly band limited signal, see, I have a signal which is not strictly band limited, but it may have some high frequency components here also, one or two high frequency components. Okay. See, suppose when I'm taking the class, rather than getting complete silence, sometimes suddenly the outside noise, something adds up, and that component may not be within the voice frequencies. Voice frequency we know will be between less than 4 kilohertz. I may get a high frequency shrill noise moving a chair, something at 6 kilohertz, another noise at 10 kilohertz. So when you don't band limit correctly, when you don't band limit, all these components will get added. And what will happen is this high frequency component takes on the identity of a low frequency component in the spectrum, in the frequency domain, not here. And when that happens, it will cause this aliasing effect. So let's see what is this aliasing effect. Usually this happens under undersampling condition. What is undersampling? Undersampling means your sampling frequency will be less than twice the highest frequency component of the message. So if you have a signal like this, rather than taking samples every TS, you will be taking samples at a much slower rate. This TS will not be 1 by 2W, but it will be less than that. So I have one sample here, one sample here, one sample here, something like that. With just 3 or 4 samples, how can you recover the shape of the signal correctly? That's when this aliasing happens, one of the reasons. See, this is the band limited signal. Rather than showing it as a triangle, we are showing it in the shape of a bell curve, Gaussian curve. This is your G of F, practical, because we are talking of practical circuits. What happens under aliasing is, you'll see this band will extend into the next signal's bandwidth. See, the next signal has started here, but the previous signal has not ended. It is ending somewhere here. Again, the next signal has started here itself, but the previous signal will be ending somewhere in the middle of the next signal's bandwidth. So you see, it is like there is a continuous mix up of bands. Each bit interval or each value, the bandwidth of each part of the signal gets mixed up. Ideally, how should it be in the frequency domain? In the frequency domain, one component here, the next component here, or they should, even if they are touching each other, it is fine, like this. Yes or no? I should have all the bandwidths either touching each other or far spaced like this. But what is happening when we undersample? Each component is extending into the space of the other component. It is extending into the band of the next component. So in the end, what happens? You are going to get the signal something like this. You see, rather than getting the signal correctly, I'm going to get a signal which is not similar to the original signal. So practically, we have two possible solutions to this aliasing. One is, prior to sampling, we should use a low pass anti-aliasing filter, which is used to attenuate the high frequency components which are not essential in the information. So what we normally do in most of the circuits, do you remember the FDM circuit? In FDM, if you remember, it was a symmetric circuit. We use low pass filter and then we use the DSB-SC modulator, band pass filter. This is to generate what? The SSB-SC signal like this. Each SSB-SC is generated like this. I was asking you why this low pass filter initially. The message itself is passed through a low pass filter, and I don't know whether you remember, I had told you that there is something called aliasing in the signals, and this initial low pass filter helps us to strictly band limit, to limit the band of the message strictly. Leave out any high frequency components in the message. It is also called as anti-aliasing filter. So if I pass the message itself through a low pass filter, that is mainly used to strictly band limit, and it is called an anti-aliasing filter. It will help us overcome this aliasing effect. Remember, this overlap should be avoided. Overlap between the bands of the successive signals should be avoided, and you should either get them touching each other at the edges, or far spaced. Lots of gap is there, then no problem at all. Either this or this is preferred, not like this. So one solution is to use a initial anti-aliasing low pass filter and remove all the high frequency components which are not essential. And the filtered signal is sampled at a rate slightly higher than the Nyquist rate. This is the second solution. What is that? Rather than keeping the sampling frequency as exactly 2W. If I'm going to consider Fs slightly greater than 2W, then I'll have this distance. Even in the worst possible case that this spectrum is extending, you would have some gaps. So your next spectrum starts here, the next part starts here. So the spectra will avoid overlap at the receiving side. Okay. So the second solution is to use a sampling frequency which is slightly greater than the Nyquist rate. Remember, the Nyquist rate is 2 times W. We need slightly greater than Nyquist rate. Okay. This also makes the design of reconstruction filter easier. So when we do this, the design of reconstruction filter also becomes quite easier. Okay. See here, we are showing the spectrum of the original signal, the basic information bearing signal spectrum G of F. And when I have used a sampling rate, which is greater than the Nyquist rate of 2W, you see there is a clear separation. And this tells us that we have to sample at a rate higher than the Nyquist rate so that you will not have this aliasing effect. Okay. And the reconstruction filter, remember I have to, reconstruction is to extract the message signal. If this is my message signal, yes or no? This is the interesting message signal. To get that message signal, the filter which I have to use, the reconstruction filter, should have a magnitude response and frequency response, something like this. In the sense, till W and minus W, it should have a flat band. It should, this pass band, the pass band of the filter should lie between minus W to plus W, right? This is the flat pass band where it is passing the signal. So the complete signal in this range is passed properly, and it should start attenuating the signals, only those signals which lie after W. So the response, magnitude response of the reconstruction filter, it's a reconstruction low pass filter because it's extracting the low frequency message signal. Should be something like this. From W to Fs minus W, this point, Fs minus W, it can have a transition band. So this filter ends here. The next filter response comes something like this. It won't take out any parts of the unwanted signal. Only required signal it will filter if these characteristics are correctly followed. Okay, so as I told you, reconstruction filter is low pass, pass band existing from minus W to plus W. Transition band of the filter is the range when it is attenuating, falling. It is from Fs to Fs minus W. Okay, W to Fs minus W. So transition band is from W to Fs minus W, where Fs is the sampling rate. Okay, all this we know. The next topic is pulse amplitude modulation, which I told you is the practical sampling process. So I think we will continue with this in the next class.